Hello, we're in Algebra 2, Chapter 7. This is Section 4. This is the first part of the second part of Chapter 7, as much sense as that may make. And we need to start talking about logarithms. And I gotta tell you, logarithms are something special. They are reverse exponents. Logarithms are reverse exponents. And this equation right here, definition of a logarithm with base b, this is the key to absolutely everything. Here's the deal. Let b and y be positive numbers with b not equal to 1. Don't worry too much about that, but it's still true. The logarithm of y with base b is denoted by log base b y and is defined as follows. Okay, so follow along. Log base b of y equals x if and only if b to the x equals y. This is very important. I gotta tell you, the thing here on the left, this is called logarithmic form. Of the equation. And the thing on the right is called exponential form. And they're always true at the same time. So this will be a bigger deal later. But if you see one form, you can trade it for the other form. Of course, that might make some sense or not without any context. So let's do an example here. At the bottom, on logarithmic form, let's see for part A here, it says log base 2 of 32 equals 5. So exponential form is 2 to the 5th equals 32. I gotta tell you, this is just so exciting. So the base in the log is the little tiny subscript, and that is still the base in the exponential form. But what's super cool is that the 32 in the logarithmic form becomes the answer in the exponential form, and the answer, or the thing on the other side of the equal, in the logarithmic form, that becomes the exponent. So there are a variety of things that teachers talk about to try to help their students understand what's going on here. One of them is kind of a mantra that it says the log is the exponent. And that's true, but it kind of sounds like something that you might say, as part of a religious exercise almost. So I don't want to go that far, certainly. But the log is the exponent because the answer in the logarithmic form becomes the exponent. With practice, you'll probably get a better grasp of it. On part B, log base 7 of 1 equals 0. That is because 7 to the 0 equals 1. Again, the thing on the other side of the equal sign in the log form becomes the exponent. Part C, log base 13 of 13 equals 1. And that's because 13 to the 1 equals 13. Now, I gotta tell you, this is not the best example ever because they have two 13s hanging around, both kind of looking lost. So let's quickly move on to D. It says log base 1/2 of 2 equals -1, and that's because 1/2 to the -1 power equals 2. Take a couple minutes and, look back and forth at how each equation comes in a pair. The logarithmic form on the left, the exponential form on the right. Don't really spend a lot of time looking at C. It's a bad example. It's true, but it's not the best, most enlightening example. But those are some really interesting things. Try the checkpoint on your own. I really recommend this if possible. So I'll wait a few seconds for you to pause it. Try the checkpoint on your own, then I'll come back and show you what's going on. Okay, for number 1, it's 18 to the 0 power equals 1. This is a lot like part B in the example, but again, most importantly, the little number in the log is the base in the exponential form, and then the number at the other end of the log equation becomes the exponent. Go ahead and try number 2 now if you haven't already. I'll wait a few seconds for you. Okay, so it's 2 to the 6th equals 64. And again, the base, the little subscript in the log equation, that's the base in the exponential equation. And then the numbers kind of flip-flop sides otherwise. That's all for page 1. Thank you for watching.